We're going to talk about tilings, which are also called tessellations. If you think about the tile that might be on a floor, it will help you understand this definition. A tiling is a complete covering without any gaps of a plane surface by plane figures. So we usually think of a plane surface as being flat. So this basically is saying if we can cover something that's flat with flat shapes and we don't have any gaps in between those shapes, we have something that we call a tiling. Now we've actually looked at a tiling or a tessellation before when we looked at this particular Escher piece. When we looked at this before, we were looking at rotational symmetry within the figure. We're going to come back to this picture in a little bit to look at how Escher was able to tile with this figure. Now we can attach some names to particular tilings. A regular tiling is made up of just one kind of regular polygon. Remember what a regular polygon is. It has all of its sides congruent and all of its angles congruent. Now, as it turns out, there aren't too many regular polygons which will tile in regular tilings. Squares will. And one way we can look at these regular polygons to see if they will tile is think about what happens when we connect them at a vertex. For example, if we look at these four squares and what happens around that central vertex, what we can see is that the interior angles of all those squares are all 90-degree angles. And since there's four of them, we have 360 degrees surrounding that vertex. That's why those four squares will tile that plane without any gaps and without overlapping. Another regular polygon that will tile the plane is the equilateral triangle. If you look around a vertex in this tiling and think about the measures of the interior angles of those equilateral triangles, all the interior angles are 60-degree angles. So when 6 of those triangles meet at a vertex, we have a total of 360 degrees. That completely covers the plane and there are no overlaps. The only other regular polygon that will tile the plane all by itself, forming a regular tiling, is the hexagon. If we think about how those hexagons meet at a vertex and look at the interior angles, each interior angle of a regular hexagon measures 120 degrees, so 3 times 120 is 360 degrees. We've completely covered the plane without overlapping. And one place that we'll see these regular hexagons used in a tiling in nature is bees building a honeycomb. As it turns out, the bees have got the right idea by using hexagons, because in doing so, what they're doing is creating a cell that has the maximum volume, but they're using the smallest amount of wax that they can to create that maximum volume. They're basically trying to balance the work it takes to build the cell versus the space inside the cell. So if we take polygons and put them together in a different way, we might have what's called a semiregular or Archimedean tiling. So what we're doing is, in this case, is taking still regular polygons, so that would mean polygons that have congruent sides and congruent angles, but we're mixing up the types of regular polygons. Plus, we're going to make sure that when we make this kind of tiling, a semi-regular tiling, that we can continue the pattern that we're creating forever and ever. So that's what we mean by extended to the entire plane. This is an example of a semi-regular tiling. It's made up of hexagons and equilateral triangles, both of which are regular polygons, and we could continue this pattern on forever and ever. One thing that you'll notice about semiregular tilings is that within that tiling, you can always pick out a group of polygons that form a cluster of polygons that we could actually repeat over and over in order to continue this pattern on forever. So in this case, if we take this hexagon and the 8 triangles that are near it, we could continue that pattern over and over again and continue to tile the plane with it. Now if we put together the regular tilings, which remember only have one kind of regular polygon in them, and the semi-regular tilings, which have more than one kind of regular polygon, put them together, we have what's called the uniform tilings. So we've already looked at this particular tiling, which we said was semi-regular. So it is one of the uniform tilings. And one of the things we're always going to be able to find in a uniform tiling is something called a vertex net. Now, here's what we're going to look at in this tiling to identify the vertex net. First, we'll identify any vertex in the tiling. So I'll pick this one. And then we're going to look around that vertex and see what kind of polygons surround the vertex. So in this case, we have a hexagon, and we have an equilateral triangle, another triangle, another triangle, another triangle. So we have one 6-sided regular polygon and 4 3-sided regular polygons. So the vertex net for this tiling would be described as 6, 3, 3, 3, 3. Each of those numbers are describing the number of sides on the polygon that goes around the vertex. Now remember, this is one of the uniform tilings, and the word uniform is really telling us something. It means that we can look at any vertex in this tiling, and we will have a uniform vertex net around every vertex in the tiling. So it doesn't matter where I pick a vertex. Let's say I go here, I can always find a hexagon that's 6, and then 1, 2, 3, 4 triangles around it. So let's go back to this Escher work. Now obviously these shapes that he's created are not regular polygons. In fact, they're not polygons at all. But we do notice a pattern here. That's because this is what's called a periodic tiling. So a periodic tiling has a pattern which repeats in 2 directions. In other words, we could look at this from top to bottom and see a pattern, and we could look at it from left to right and see a pattern as well. So when we're looking at these periodic tilings, we're probably going to notice that there seems to be something that's repeating, but how can we really tell if the pattern is periodic? Well, one thing we can look for within this pattern is something called a lattice, and you might actually be able to see it already within this particular picture, but let's make it a little bit darker. So the lattice is really made up of parallel lines going in 2 directions, which create quadrilaterals. In this case, it looks like those quadrilaterals are squares. And what's important about that lattice is that it's defining these quadrilaterals, which we're going to call the fundamental regions. So each one of the quadrilaterals is showing us a fundamental region for this particular tiling. Now, if we take that fundamental region and we duplicate it, we can create the rest of the tiling. We may have to rotate it, we may have to reflect it, we may have to translate it, but we can take that region and we could pick any of the rectangles that we see because they are all identical, and we can move it. So we could, let's say, rotate it to here, and you can see that the pattern repeats. Or maybe we could rotate it and translate it down to here. Now remember, this is a piece of art, so there's some coloring that's going on. We're not looking at the coloring in this case, we're looking at the outline of the figures. And you can see that the pattern that we can see in that fundamental region is repeating in every part of the lattice. That's always going to be the case with a periodic tiling. Now, if we've got this lattice, that means we've got some sort of quadrilateral. And all quadrilaterals can be made to tile a plane. Now, obviously, if we have squares, squares do tile a plane. But so do rectangles. And there are many, many, many different quadrilaterals that we could use to tile a plane. In fact, we could use some quadrilaterals that look a little bit unusual. So we're going to do that now. We're going to look at a website and play around with a few quadrilaterals to see if we can make them tile the plane. Okay, so we've got what looks pretty much like a rectangle here, and we know that that would tile the plane. But let's take this and make it something that, well, we'll distort it pretty much. So I'll put an obtuse angle there, and in fact, let me take this and do that. So we'll make this a concave figure. So we still have a quadrilateral. It's still got 4 sides. So the question is, can I make this shape tile? So let's try this. What if we copy that shape and rotate it? We could fit it right here. And I'm going to copy it again and rotate it again. That would fit right about there. And let me just copy the original. I could make that go right here. And I copy and rotate. I can make that one go here. Let's just copy. And you see what's happening. I'm able to, through either just copying and translating to a different place or copying and rotating, I'm able to make these quadrilaterals fit together. So any quadrilateral could be used to tile the plane. So let's go back to some of Escher's artwork and see what he did to create these figures that he did. So we know that there's some sort of fundamental region that he must have started with. And in this case, what he started with was a square. And he took some shapes and cut them out of one side of the square and then just translated those shapes to the opposite side of the square. And in doing so, he was able to create these shapes that would tile. Now, translations aren't the only way that we can take a region that will tile and create these shapes that will tile. Take a look at this one. Can you figure out what shape that fundamental region must have been? Well, in this case, in order to get that lizard, he started with something that would look like a parallelogram. And he did something similar to what he did in the last one, in that he cut out shapes from one side and translated them to the other. But then he also cut out shapes and rotated them around the center of one side of the parallelogram. So he translated, and then from a center point, he also rotated. So now this particular piece is actually combining a lot of the things we've talked about. First of all, in order to make this particular tiling, he had to start with a shape that would tile. And we said that there are 3 regular polygons that will tile. The square will, the equilateral triangle will, and the hexagon will. In this case, he started with a hexagon. And then he took that hexagon and he altered it by rotating some shapes. So he cut some pieces out and rotated them around 3 of the vertices of that hexagon. And that was how he created the legs and the tail and the head of the lizard. So we'll get a chance to practice some of this in class.